Hello, everyone. This is our fourth session of our brown bag sessions. Today's topics are going to be about physical habitat. We've got three presentations today. So let's go ahead and get started. Ruben was going to be the first presentation, and he's going to be talking about physical habitat to flow, I believe. So Ruben, the floor is yours. You should have ability to share your screen.
That's right. Well, thanks, Chris. I hope you all can see this. I've only got one screen, so this is it. Right, I'm presenting some results of effectiveness monitoring of habitat in the restoration reach of the Trinity River. I just want to acknowledge the many people that worked on this project over the years. I recently started with the Fish and Wildlife Service in March and have been as a fish biologist and have been getting caught up to speed about all of this work that's been going on. It's quite a lot of work. I'm very impressed, and just wanted to acknowledge all the agencies in the upper right corner here that are involved, quite a few agencies, and all the people that worked on this presentation. Josh put the slides together for me, and the others that have put all the field work and other analysis into this effort. It's a good title slide too to show in context what we're talking about. It's the Trinity River in Northern California. We got quite a few restoration sites that we'll be focusing on and how those have changed over the years, and we're focusing on habitat for juvenile salmonids, particularly Chinook and coho. The U.S. Fish and Wildlife Service, from what I understand, this is a part of the adaptive management plan. And this particular study is focused on the evaluation and monitoring parts of the adaptive management agreement. For those of you who don't know, the restoration reach in the Trinity River is defined downstream of Lewiston Dam to the North Fork of the Trinity River, 64 river kilometers. The history of the Trinity River is it experienced quite a bit of disturbance early on, particularly through hydraulic gold mining for gold resources in the river, which created, as any of you have seen, large spoils of gravel on the banks, and then the creation of dam as an impoundment. As a fish biologist, I can look at the history of salmon in the river. It doesn't look good. Clearly, there's some correlations there. Pre and post dam numbers. Not to mention the harvest, but yeah, there's quite a bit of impact there. 96% reduction in coho, and significant reductions in other populations. From a study that was done in 1999. This inspired a river-wide restoration program, and there's multiple parts of that restoration program, including sediment augmentation, gravel augmentation, adding spawning gravels to the reach, water year specific flow releases from the dam, and then mechanical channel rehabilitation, which is what we're focusing on here, creating side channels and adding wood to the channel and creating better habitat for rearing of the juvenile salmonids. In 2005, the first rehabilitation sites were completed, and so that initiated some monitoring programs in order to we wanted to quantify how much habitat has changed, and we also wanted to find where in the channel that the habitat has changed, and whether or not it has withstood the test of time, and how does that change over different flows. To do that, it's been quite a large effort and a field-based effort. We have with the Fish and Wildlife Service, at least there's two sort of parts to this evaluation. One is focusing on these restoration sites, which is pre-construction, post-construction, and then we revisit the sites 3 to 5 years later after post-construction as well. There's another evaluation going on that's more of a systematic approach to measuring habitat across the entire river, not just the rehab sites. And they're randomly selected grid sites with a standardized scale of 400 meters, which Josh will be talking more about later this afternoon. At the rehabilitation sites, in order to measure these changes, we had people on the ground and physically measured them on the ground with flow meters, GPS mapping tools. And we use those field results to classify habitat in terms of what we know juvenile salmonids can live in. The range of depths and velocities, and also distance to cover habitat is very important for these small fish. And with those metrics, those minimum and maximums, we were able to classify habitat in kind of a matrix where our optimal habitat is areas that have satisfied depth, velocity, and cover requirements of juvenile salmonids, and suitable habitat classifications, which can include just cover habitat that might not satisfy the depth and velocity requirements, but also no cover habitat that actually satisfy the distance to velocity requirements. And then, of course, without distance and all those outside of it was considered unsuitable. In our analysis, we looked at how optimal habitat changed over flows and time before and after construction, and then total habitat, which is suitable habitat in addition to optimal habitats. That's the total habitat. With coordination from our water release friends at the dam, they were able to hold these flows at specific times for our field crews to go out and collect all this information. These are the flows we were able to collect habitat data on. 2000 was as high as we could go, just for safety reasons for field collection. As far as quantifying the amount of habitat and how it's changed, this is a graph we used for all 13 different sites at summer base flow. We're just looking at a single flow here, and this dark line, vertical line here, indicates the year this particular site was constructed. I'm not sure which site this is specifically. We got 13 of these graphs. And to quantify, we took the amount of hectares from what we surveyed before it was constructed, and then the year or so after. And these graphs show total, like I said, the suitable plus the optimal, and then just the optimal as well. And then the difference between these two is our metric that we use to quantify. Through all 13 sites, total and optimal habitat, there we found significant increases in total and optimal habitat, both before and after construction, which is fantastic. I mean, it's a great metric to show that all that work that's been done is significantly improving the habitat for juvenile rearing in this restoration reach. Fantastic result, in my opinion. We wanted to go a little bit further and look at how changes happen with flow. In order to do that, we wanted a little bit more focused, a little more standardized way to quantify change over time. That involved compiling multiple layers in order to focus our efforts. Wanting this first is the extent of a restoration, entire extent of a restoration site. And then, as I mentioned before, we had our systematic sampling, which selected at random sites to go and visit and estimate habitat, which you can see is a dark line. And these two just so happen to be right next to each other. That's the nature of the random selection process. So we wanted to have areas that were part of a restoration site that also were selected for the systematic sampling, and then also overlapped restoration features like side channels, cover largely debris structures, and that's what these polygons represent, these overlapping polygons. And those areas are what we targeted for the analysis. Is a little bit easier to look at. And then if you continue along our selection process, it focuses in on these areas that we used for our trend analysis that included all those layers together. A little example of the results here in this table. We have our total pre-smolten in square meters, the year constructed, and also the survey year we collected. So in particular Loden here, it was constructed in 2010. So we got the pre-construction estimates, and then while construction, then after. But then also we went back a couple more years to quantify the trends over a little bit longer period of time. There we go. And yeah, just to remind you of the graph that I showed earlier, we had a couple more visits to this site, and then the metrics we're using are the difference in total habitat and optimal habitat between the year after construction and then the most recent year of revisiting. So this detail in here is not quite included in that, but it also these revisits help see the trend a little bit better. Those results showed us about 50% of the sites continued to have more habitat, and habitat continued to increase at the most recent survey. We got a lot of symbols here and a lot of sites, so don't get your eyes crossed on that. I think that the most important thing is that about half the sites still showed was continuing to have more optimal habitat than and total habitat than pre-construction. So that's great news. The other end of it is that about half of the other sites experienced kind of a decrease in optimal and total habitat up to 5 years after the post-construction survey. We wanted to look a little bit further into that and see those trends and how it changed over stream flow, multiple stream flows. In order to do that, because there's so much work, we had to focus our efforts on six sites in a range from 300 to 2,000 CFS. That was what we could get out there for. This is kind of a matrix here of the sites and how and the years that they were selected for survey. So there's quite a bit of a range here, 2000 to 2017. And like I said, the metrics we used to estimate habitat were from the most recent survey, by subtracted by the survey after construction. These are highlighted here just because they kind of Lower Bucktail and Bucktail became one site after construction continued in 2016. Just wanted to kind of point that out, that those sites are right next to each other and together, and so the metrics for these were used 2017 to 2015. Another, this is just one example of the flow to habitat curves that we used to compare. the years on each curves, you can see with the discharge increasing and focusing on optimal pre-smolt habitat area. It becomes challenging to compare these curves exactly to find a metric to at all these different flows at different times and different areas. And what we used is a metric called area under the curve, AUC, which takes the difference in the x-axis and divides it by where the y-axis is, and adds those together to create an area, one number for each of these curves that then we can compare between years and plot those out and determine statistical differences there. What this is the spread over those six sites, and what those AUC values show. The lines are connected to are per site. So this one line right here, pre-construction, a great increase for sure. With discharge, all discharges in AUC, mostly all these are increasing, which is again great news, a great metric. They're all going up pre and post construction at all flows. So they're holding up as far as habitat goes throughout those flows that we measured. And as far as we wanted to continue going on after and see how the sites continued to measure up after construction, and we did the same AUC procedure with post construction and then another site revisit. That's not quite as great to see. We're looking at not very many sites here, but only 2 of the 6 sites actually continued to have more habitat than most of the surveys. So we're experiencing a little bit of decline as the years go on, just a little, but still even higher than what we started with. So I think that's really the most important thing to focus on here. As for our agency, and it's obviously going to create some questions. Well, what's happening at these places? Why is there a slight decrease in optimal habitat in some of these sites? Hop and total. Where is it happening? And we're able to, because we got all the sites, we have all this information. We can focus on a few particular examples. For example, the triangle site here increased dramatically, continued to increase after the site revisit, whereas Lewiston Cableway experienced a little bit of a decline. If we use Cableway as an example, we just look at before and after shots. What in this example, what happened was some of these constructed gravel bars that you can see here in the aerial photography have changed. A little bit has washed away, and it's gone. I mean, the gravel has gone somewhere, but for this site, in our analysis, this is what happened is almost 80% reduction in the area of these point bars, which then in effect created a decrease in total pre-smolt habitat. Conversely, if you look at upper Bucktail, for instance, we had a dramatic continual increase in optimal habitat after the site revisits. In this particular example, it was the deposition of gravel. In 2000, I believe there was gravel augmentation put into upper Bucktail, and then we had a large flow event in 2011, which displaced a lot of gravel into this and deposited into this site, which created optimal spawning and rearing conditions for juvenile salmonids. And I think this is a before and after shot. You can see here the augmentation was the gravel was added, and then as flows increase, it was deposited in this large area here, and the area of optimal and suitable habitat just continued to increase. So there's kind of a push and pull, which rivers are very dynamic. This is typical. That is what happens. So offers a little bit of an explanation on why some are increasing and some are decreasing in optimal habitat after construction. I think the biggest point in these results is that the construction is really doing a fantastic job at creating more optimal habitat in this restoration reach, both through before and after, and then sustaining flows, increasing in flows. But they're not quite sustained. There are some features that are not holding up, withstanding the test of time over 5 years. And the question begs, I mean, should we go back out and start measuring and continue to look at the trend? Does it continue to go down? That's probably good information to have. Or does it start to come back up as the river starts to balance itself out and create this dynamic environment of scouring and deposition and that sort of thing? It's a question that we are asking ourselves. Like I said, I just want to drive this point home. Before and after construction, significantly better. I think what is also interesting is that even after these site revisits, if you look at how discharge increases, these curves kind of match. They still match each other. So even though the in 2017 has been, the habitat is a little bit less than 2011, it's following the same trend through the flows, which means that there's still amount of stability there that we can rely on. I also wanted to point out about this, the curve here, the habitat dip, that it seems to be a topic of conversation. What's happening there? Why does habitat decrease as flow increases? That seems counterintuitive. That doesn't make a whole lot of sense. What's going on there? And if we look again, take just specific examples of specific sites, we can kind of get an idea of what's happening. And if you look at all these colors, I believe the blue is optimal habitat. As you increase the flows, as we go here, the flow is going in the down from right to left. So that's the direction of the flow. You start to increase flow. The flow comes to the side channel, and about that flow, you start to see a reduction in the amount of optimal habitat from low flows, and that's particular velocity, most likely velocity, but also can be depth. But then as you continue to go up along the discharge, all of a sudden what happens is you have a dramatic, the optimal habitat just changes location. As the water breaks the bank and comes into the floodplain, you have a large amount that's available to these juvenile salmonids to rest from the flow and to feed and forage, and therefore creates a lot more measurable habitat. Definitely some things to think about. I'm not quite sure what to do about that, but this is I think it's important to explain and to show that this habitat dip, we have reasons for it, and I think it's just worth pointing out that it comes back up after the water breaches the bank and into the floodplain, which can inform other restoration activities. Maybe a site design can improve those floodplain areas. We can focus on those rather than side channels. I'm not sure. Where we're going with it now, we have a solid hydraulic model across the entire river, and that's what we're going to start using to monitor these sites, which is a lot more convenient. It's a lot easier to use a hydraulic model rather than having people on the ground and coordinating all that. And we had some results from those, which is we can compare with the hydro model. We can compare that is actually what was designed or what was intended at these sites with how the habitat was increased or decreased pre and then after construction. There is a little bit of deviation there. What's nice, what I just want to this slide is just to show how we can actually compare, and we have a metric. We can compare how our designs are matching up with what we're actually seeing on the ground. Some some are more deviated than others, and we can also see how that is distributed over space. Some of these sites, where are the deviations happening? This is differences from the design versus what we're seeing with the hydro model after construction. Things just, if you just look at the color, how the colors change from left to right. This is now capacity is what we're measuring here with the hydro model. We've shipped from strictly area to actually capacity because we have the hydro model now. So a little bit different metric there, but it kind of means the same thing. Capacity is kind of decreasing in these channels in these areas, and most of all down here as the design. The design was to have the optimal habitat being this little side channel here, where as built, what we measured is actually that more the habitat, optimal habitat is more up here in this side channel with a little bit of disconnect there. That's just where we're going with it. Yeah, thanks to everybody that was in charge of this. I hope I explained it well, and I'll take some questions, but I might have to punt over to Josh if they're too hard.
Thanks a lot, Ruben. If you have any questions, go ahead and raise your hand and we can go on. Or if no one wants to raise their hand, they can chime in as well. We got to have someone.
Right, I didn't do that good a job. Come on.
So one thing I have, Ruben, is you talked about the kind of the time period of which we need to, revisit it in the fish world, and directly relating to salmonids in the IAP. It says we can expect to see changes in something like 3 or 4 generations of salmon. Is there a time frame of where you would expect these habitats to kind of physical habitats to kind of stabilize, or what's kind of the time scale we need to revisit some of these, do you think?
That's a really good question. I'm not a geomorphologist, certainly, but I do have to consider those in terms of fish biology. Absolutely. And that's part of the question of whether or not we have to continue to monitor these sites, whether or not. I think we do. I think we need to consider continuing to monitor and looking at curve and those trends to see if they do go down or up. I'm not sure on other places. I think the Trinity, this is one of the largest restoration efforts in the country right now. I'm not sure if there is a whole lot of information on how long we should expect it would take for those sites to stabilize, and they're designed to kind of be self-maintaining. I believe I know that they're designed to be scoured in some areas, but then have them deposited in the areas within the site. And that's certainly something to consider, and that's part of the reason why we visited the sites when we did, up to a year afterwards, just after a season of flow, to see if the expectation stood up, and then over time. So I mean, it's a really good question.
This is Josh. I'll throw my little 2 cents in. So you said 3 to 4 generations, so what, like 9 to 12 years, something like that. Well, the longest time period on this study that Ruben just presented was 12 years, but that was only for one site. The other ones are, less than that, 5, 6, 7, 8 years. The year this study stopped looking at the data, or the data was collected in 2017 was the last year. So that's already, 4 or 5 years on from that point. So, I mean, I would think it'd be worthwhile to to reassess these sites, you know, any time now.
Go ahead.
All right, Kyle, I see your
Kyle?
hand up. Go ahead.
Yeah, I guess along those lines of reassessing in the future, I was wondering if the Habitat team has done any kind of comparison with the predictions from the hydrodynamic models that could be directly compared to the long-term data sets for the mapping criteria, and if that's possible, or if the models represent what was observed on the ground, or if there's any plan in the future to do that.
Sure, a little post.
I certainly think that's worthy of trying to come up with a methodology to compare predictions from a hydraulic model to you know, mapped habitat, but we certainly haven't fleshed anything out, you know, yet.
I mean, the question would be, they might have changed too from whenever that model was calibrated. You know,
we did do it back in 2010. We weren't using SRH2D at that point. It was just the 10 hydraulic models that we developed at random grid sites. It has not been done as a comparison against the latest 40-mile models, but it could be using the same methodology.
Thanks. Yeah, I mean, it's just a peril of advancing technologies is things become your time series over which you can compare things changes depending on the methods or technology that was used to collect the data. And the longer we can make these time series across different technologies or data collection methodologies, the more they're going to be able to tell us.
Yeah, I agree. You know, one of the things about this was it's kind of a trade-off, right? So we adopted the hydraulic modeling platform to try to align our methodologies with what's used in the design process, but obviously that creates a challenge to you know, compare to previous data sets. So
Go ahead, Brant.
Okay, there you go. Yeah, I was just wondering, you know, can you explain why, Ruben, why you think that we see these decreases in habitat over time? You know, the projects, and you know, this kind of gets to what Kyle was asking about. You know, we design them to be self-maintaining and certainly nowadays, hopefully to increase in habitat over time. Why do we see this continual, we see the habitat dip and we also see decreases in habitat over time? What do you think?
the two examples that Josh put in the presentation are pretty good. I mean, they scour and not necessarily deposit the gravels within that site. So the gravel went somewhere, it got deposited somewhere,
Right.
just not necessarily within the site. Certainly displacement of wood, largely debris, the way that, I mean, cover habitat is very important for juvenile salmonids to avoid predation. And if you got a big flow or something and that all of a sudden that big log got, you know, dislodged and flowed downstream, that's a lot of area that you lose.
Yeah, that makes sense, right? You know,
So maybe you got to, yeah, they figure out a way to anchor the wood a little better, or, you know, those are all just.
well, I think about what we're doing now, and I do think that, you know, we're hoping to get vegetation growing in these wood jams so that the vegetation stays, and the example at the cableway that, you know, we skeletal bars are being used now so that maybe we won't lose all that gravel. Anyway, those are,
Yeah, that's part of the adaptive management process. That's the whole point, is to go out there and actually see what change is happening, and then adapt, and then continue to improve. and I think it's successful, especially in this analysis for sure.
Right. Thanks.
We have time for probably one more question if anyone has one. If not, we can move on.
Nice job, Ruben.
Yeah, I'm not seeing any more hands, so thanks a lot, Ruben. Great job. This is a good introduction to the program, I guess. And we have up next Emily and Dave, who are going to be talking about the fish habitat capacity synthesis report.
Everyone, thanks Chris, thanks Ruben, nice job. Let me just share my screen. Okay, can everyone see the presenter view?
Yeah, we can see it, Emily.
Yep.
All right, actually, Aaron's gonna start us off with a little introduction, and then Dave and I will take over.
Thanks, Emily. Thanks, Chris. So hey, everyone, my name is Aaron Martin. I've been a fisheries and habitat biologist working on the Trinity for the Yurok tribe for the last 20 years. So I got a lot of history, especially in terms of rearing habitat with the program. And, we're here talking about rearing habitat today. It's been a main focus of the restoration program through this time. And the program's really we're interested in understanding habitat at multiple scales. And Ruben just did a great talk talking about the site-specific scale. And that's something that we've done a really pretty good job of over the last 15 years, is evaluating rearing habitat at these smaller scales, at site scales, looking at restoration projects and how are they changing through time. As good as that's been super valuable, and it's provided that real-time feedback, not just to the design team, but to the program and everybody about what we're seeing and what's happening out there. But there's still limitations to that effort. It's where we specifically can look, and it's at the specific range of flows that were out there. Of course, we'd like to know everything. We want to see it. We want to understand it everywhere, and so we care about habitat at a larger scales as well, like not just restoration sites and specific flows, but the full range of flows and the full project reach. And so recently, in the last few years, we have new tools, new data sets coming available that are giving us opportunities to look at habitat in ways that we haven't had before. Specifically, we have 40-mile models we have really detailed terrains. So like 3D images of the 40 miles and really great hydraulic models so we can estimate depths and velocities at a full range of flows anywhere in the river. And along with that, we have a habitat capacity model. And this was developed essentially through snorkeling, through thousands of observations of our crews in the water, observing fish and describing the places and numbers of fish that were the areas they were using. So this tool that's developed for a different reason, it's called the fish population model or production model. We can use that here and to evaluate habitat, and we can look at it at ranges of scales. We can look at whole reaches. We can look at sections of rivers we've maybe manipulated or not at ranges of flows that we haven't had available to us before. So it's a new data set. We're really excited. Emily and Dave have done a lot of work on this, and we'll let them take it from here. Thanks.
Thanks, Aaron. Okay, so we approached this report in 4 objectives. Our first one was to evaluate habitat capacity in rehabilitated versus non-rehabilitated areas. The second objective evaluated habitat capacity between sites. In objective 3, Dave evaluated physical metrics related to habitat capacity. And finally, we evaluated capacity related to flow frequency and duration. So brief methods overview. The capacity model was developed with many people's work, and the capacity model was written up by Song and others. This model provides estimates for number of fish at a range of flows using conditions of depth, velocity, and distance to cover. And then we utilized this model output in a GIS format with tools developed by Nate Bradley. We then identified a range of flows appropriate for capacity evaluation of juvenile Chinook salmon. The model output provided estimates from like 150 CFS all the way up to about 20,000 CFS, I believe. So we didn't want to use that entire range. And then we wanted to identify reaches or different spatial scales for evaluation. And then finally evaluate capacity. So the Trinity River Restoration Reach here is depicted in 7 reaches. These are known as maximum fisheries flow reaches identified in a previous report by DWR. As you can see in the map, they are varying lengths, and they have various numbers of sites in them that are denoted by the areas outlined in black. But these reaches mostly depend on tributary contributions, making them hydrologically distinct. So the data we had for this analysis are as recent as 2016. So there are 5 sites that were built since then that are not included in this analysis. Prior to 2017, about 1/3 of the entire restoration reach length had been rehabilitated in these 24 sites. These reaches also have a varying number of sites, like I said. And note how reach 7, the downstream-most reach near Junction City, it has had quite a bit of rehabilitation. And this will be good to keep in mind when we get to comparing its capacity to other reaches. And then you can also see in R6 here, it only has 1 site, which equates to about 10% of its length rehabilitated. But all of those 5 sites built since 2017 have occurred in that reach. So one of the first steps we did, like I said, was to determine a range of flows for evaluating capacity, and also to identify a rearing period for juvenile Chinook salmon. So we identified that rearing period as January 1st through May 31st. We then developed daily flow duration curves over those rearing months for each of the 7 MFF reaches. And we found that flows are less than 99.1%, flows are less than 99.1 CMS for 82 to 91% of the rearing period. So flows greater than 99.1 or about 3,500 CFS are pretty rare during that rearing period. So therefore we determined a flow range of 4.2 to 99.1 CMS for evaluating capacity among these reaches. So using a similar method as Ruben described to compare capacity flow curves across different scales, we used the integrated area under the curve, which we termed I in this analysis. And then we normalized I relative to either reaches or sites being compared to each other. For example, the MFF reach with the highest value would have an I sub n value of 1.0. So we first summed the capacity and normalized it in fish per meter for both fry and pre-smolt within the entire area of each sub-reach. We plotted that here. And you can note there is a habitat dip in these curves. And they're also listed, R1 through R7 is upstream to downstream. And you can see how from the I sub n values, the decrease in capacity as we move downstream. So then getting to the real point of objective 1, we compared rehabilitated versus non-rehabilitated capacities. In these plots, the solid lines represent non-rehabilitated areas, and the dotted lines represent rehabilitated areas for fry, expressed as fish per meter. You can see that rehabilitated areas had greater capacity than non-rehabilitated areas in 4 out of the 7 reaches. And you can recall how R7 has about half of its reach rehabilitated, yet capacity is lowest, and there's very little difference in the rehab versus non-rehab areas. It is worth recognizing, however, that R7 includes the very first 5 projects ever done prior to any in-channel rehabilitation techniques. So moving to objective 2, we took a closer look at non-rehabilitated capacity versus rehabilitated capacity at the site scale, with, again, in these plots, non-rehabilitated curves in solid lines and rehabilitated curves in the dotted lines parsed out by site. And to quantify how capacity has changed and the habitat has responded to rehabilitation, we evaluated the minimum capacity, or what we call C-min, which is the lowest point on the curve. And a difference in C-min in the rehabilitated versus non-rehabilitated areas suggests how rehabilitation has changed capacity. So you can see how C-min takes on a lesser magnitude of capacity and occurs at a higher discharge in some cases farther downstream than in upstream. So in this plot on the left, we compared the flow associated with C-min at rehabilitated areas on the bottom and the flow at C-min in non-rehabilitated areas on the left. And so where restoration is successful is in the shift of C-min from a higher flow rate in this non-rehabilitated area to a lower flow rate in the rehabilitated area. And so this plot shows where that shift has occurred, where these points deviate from this one-to-one dotted line that represents no change. So we ask, has C-min been affected by rehabilitation? Most notably in sites among reaches 2 and 4, and then also in general, more so in the upper river than in the lower river. So as the rehabilitation goal, C-min needs to shift up to a greater capacity and to the left to a smaller flow in those rehabilitation curves. In other words, put more simply, we need to remove the dip in the curve. So this slide represents that normalized integrated area of capacity by site, going from left to right, upstream to downstream. And we wanted to point out how you can see, again, that general declining trend. However, there is variability. Also, reaches 3 and 5 are canyon reaches. However, reaches 6 and 7 at the downstreammost end have similar capacity to those confined reaches. However, 6 and 7 are not confined. They're in unconfined valleys. And then it will also be interesting to see here in Reach 6, once the most recent 5 sites are evaluated in this way, to see how this trend may change. So with objective 3, I'll pass it off to Dave.
Great, thanks, Emily. Can you hear me? Yeah?
Yeah.
All right. Physical complexity has been a restoration objective in the Trinity world for decades, at least as far back as the flow study years. But we still struggle to define what complexity is or how to measure it. So here we're going to evaluate a few proposed complexity metrics and relate them to habitat quality as measured by capacity. Now, a general definition of physical complexity might be something like morphology that supports variable conditions in space or time.
Hey, Dave.
Yes.
You're a little muffled. You're a little hard to hear.
Oh, really? Let me see. What can I do
Is that just me,
that?
or
Is that better? Does that help? No?
You're still a little quiet, Dave. Maybe a little closer to the microphone.
Oh, I'm right here. I can't really get any closer. I'll be spitting all over my screen, Okay, I'll try to speak up louder. Anyway, it's important. We think it's important to remember that habitat quality changes with and depends on fluctuations in discharge over time. So that's why I mentioned that, both space and time variability. The first variable that I want to talk about is R star. That quantifies topographic relief in the channel and the near channel area. Is computed from depth percentiles as shown in this equation, where the depths are measured from a reference discharge of 56.6 cms, which is 2000 CFS. Now, fish habitat's wet, so changes in what's wet as discharge changes define variable habitat conditions in the time domain, as well as over a wider spatial domain. So that's quantified by the mean wetted width as a function of discharge, symbolized by W, and by the integrated area under the width to discharge curve up to the reference discharge, and that's symbolized by I sub WR. And we're going to compare those variables, those metrics, to the following habitat variables. C sub R is capacity measured at the reference discharge. I sub R is capacity integrated under the discharge curve up to that reference discharge. And then P sub 0 is the fraction of the wetted area at the reference discharge that has 0 distance to cover. Okay, next slide, Emily. Can you advance the slides, Emily? Oh, great, thanks. These graphs show wetted width plotted against the discharge in the 7 maximum fishery flow reaches. These plots extend to a discharge of 170 CMS, and that's 6,000 CFS. In reaches 1 and 2, plotted on the left graph, W begins a bit more, or width begins at a bit more than 30 meters and increases to, with discharge, to about 75 to 90 meters. In the middle graph, that shows reaches 3 and 4. Their width begins at about 30 meters, increases with discharge to about 60. So, 60 meters. So it's a little narrower. And then reaches, 5, 6, and 7 plotted on the right are much narrower. The width begins at less than 30 meters and tops out at about 50 meters. So go ahead and click it, Emily, and give me that. There it is. Pop up that thing. So you can see that this mirrors the capacity curves that Emily showed a little bit, a few slides back. Reaches 1 and 2 are up on the top, 3 and 4 are in the middle, and 5, 6, and 7 bring up the bottom. Let's go to the next slide. Okay, so plotting wetted width directly against capacity, however, doesn't work so well because width always increases with discharge, whereas capacity has that characteristic dip, especially in downriver reaches. That's illustrated in the graphs on the left, which show fry and pre-smolt capacity plotted against wetted width. And they just, you can't really, fit a linear trend to that. But the graphs on the right show that that the right limbs of the capacity to width curves, that is that, you know, when the data to the left of the dips is removed, that there's a linear relationship there. So the inference of this result is that width is a primary factor that determines habitat availability as water spreads beyond the low flow channel area. Let's go next slide. Okay, the graph in the upper left here shows that fry capacity integrated to the reference discharge, which is plotted on the vertical axis there, is strongly correlated with integrated wetted width. So, you know, I mean, that's Pearson's correlation coefficient there, 0.96. Don't worry about the other graphs on this slide. I'm not going to take the time to explain them. So let's go next slide. Okay, so now moving on to topographic complexity, R star. The top two graphs here show fry and pre-smolt capacity at the reference discharge plotted against R star, and the bottom two graphs show integrated fry and pre-smolt capacity versus R star. They show the integrated under the curve version of those, okay? So, and the correlations between R star and all these capacity measures are very strong in all cases. Let's go to the next slide. This table shows correlation coefficients for relations between complexity metrics and variables that represent the main ingredients that go into the computation of capacity. Those are, you know, those being mean depth and mean velocity at the reference discharge, and the fraction of the wetted width, the wetted area with zero distance to cover at that discharge. Both R star and integrated width are strongly correlated with the availability of cover, you know, like in the, you know, better than 0.9. And they're inversely correlated with mean depth and mean velocity. So in short, this table says that topographic relief, wetted width, and the abundance of cover elements, they all covary together, those three. And that increases in any of those elements correspond to lower mean velocities and lower mean depths. Now it's interesting to kind of think about causation here. Topographic relief and cover evolve together. You know, we can't say which is the chicken and which is the egg. You know, cover elements like vegetation can encourage deposition, which can increase relief. Conversely, topographically higher areas are more likely to develop vegetation. Meanwhile, wider inundation zones present more space for those processes to occur in. Okay, next slide. Okay, and finally, I just want to stress that spatial scale matters when evaluating physical complexity. These four graphs plot fry and pre-smolt capacity at the reference discharge and integrated capacity versus R, just like in the previous slide I showed you with four graphs. But now R star is computed for 24 shorter reaches. These are the river corridor reaches defined in the 2015 report. The correlations for these 24 shorter reaches aren't nearly as strong as they were for the 7 maximum fishery flow reaches. That's because shorter reaches, you know, equal smaller samples of morphological units that can be more strongly influenced by atypical channel morphology. You know, like for example, the red symbol in the graphs, which and it plots with a really large residual from the best fit line in all four graphs, that corresponds to a reach that contains Rush Creek Pool. That pool, which accounts for a sizable proportion of the reach length, contains a long stretch of deep, low velocity water that scores really high on capacity, even though bed relief is pretty low. So these complexity metrics, and I'd argue complexity metrics in general, are best applied to stream reaches that span multiple geomorphic units. They're not really usefully applied to very short stretches like the grits panels used in some of the habitat studies or the rehab site scale that's considered in other sections of this report. So that's that, and I'll hand it back to Emily.
Okay, thanks, Dave. So moving on to objective 4, we wanted to evaluate how capacity changes overflows given in a given water year and with accretionary flows downstream. So in these plots, we took the capacity or C values that correspond to specific flows, interpolated C between flows, and then plotted those C values with the hydrographs from selected dry, wet, and normal years. So depicted in the plots, the hydrographs are in the black lines, along with fry capacity and pre-smolt capacity in the light and dark gray areas. And then within the red area shows the rearing period from January through May. And so the point of these plots here, I think, is really the timing of base flow management, how it coincides mostly with the fry life stage in winter months, thereby limiting any fry capacity and subsequent pre-smolt abundance. So taking that concept one step farther, we then plotted flow-specific estimates of C as it corresponds to flows in a flow duration curve. So this figure represents capacity, what I call capacity duration curves for the entire restoration reach, with C on the y-axis related to daily flow exceedance probabilities from the flow duration curve on the x-axis. So the capacity duration curve for current base flow management is in the black dotted line, along with a series of curves representing alternative base flows over the same duration, but with increased magnitudes. So we calculated the percent change in fry capacity over the entire restoration reach by integrating the area under the capacity duration curves. So to do that, we found the smallest C min among all these curves to calculate I base, subtracted that I base from the entire area under the curve to get I sub D, and then found the percent change in I sub D. And this way we attributed the capacity increase to flow management and not to C min from channel form effects. So as you can see in this table here on the right, there's no substantial increase in capacity until dam releases are greater than 28.3 up to 56.7 CMS, or which translates to about 1,000 to 1,500 CFS. So it's important to note that this increase does account for accretionary flows throughout the reach, the entire restoration reach, from increasing base flow magnitude over the same timing and duration as current base flow management. We recognize that this kind of static flow rate is, for a flow management change, is probably unrealistic, just because this is during winter months when flows are naturally more variable. However, these estimates are meant to provide some insight into potential capacity benefits from changing flow management, to quantify how capacity responds to the timing and duration of flow management, and that this approach can be applied to any alternative hydrograph or scenario. So in summary, we found that flow management and accretionary flows can create bottlenecks in capacity. We also found physical bottlenecks to capacity from channel confinement, mostly in downstream reaches. Reaches with greater wetted widths that occur with frequent flows provide more habitat than reaches with less wetted width. Actually, across all flows, excuse me. We found that topographic variability increases capacity at low flows. And as Dave described, topographic variability, wetted width, and abundance of cover elements vary together and contribute to capacity. We found that rehabilitation sites with the greatest capacity have an elevated C min value, at lower flows and greater wetted width at low to mid-range flows. And finally, we found that rehabilitation has been effective at increasing capacity in most reaches. However, the impacts are differential among reaches, which suggests that there may be more appropriate techniques for rehabilitation in those reaches. So finally, we recommend to continue using these massive data sets in such extensive ways as we have here. We found several issues through this process in existing data and we're able to correct them. We found, or we recommend that restoration efforts and habitat assessments focus on features at less than 99.1 CMS because they are ecologically significant flow duration inundations. We recommend also focusing in downstream reaches to increase the wetted width. To continue evaluation in sites built since 2017. And we also recommend evaluating the physical metrics as guides for habitat design and management. Those physical metrics, they really have a knack for describing the complexity, diversity, and dynamism, and the strong correlation to biologically relevant values across different spatial scales and geomorphic settings. And we also recommend to manage flows that would increase capacity relevant to the timing of those rearing life stages. And finally, we recommend continuing these evaluations over time and also evaluating fish use in lotic and lentic environments. And to continue these, the fish use with these physical variables, but also with other important variables to rearing fish like temperature and food availability. So with that, thank you for your time. We thank TRRP, our reviewers, and shout out to Nate Bradley for all his help in the GIS tools. And with that, we'll take any questions.
All right, thanks. Good job. If you have a question, go ahead and use the raise hand feature, and we'll.
I want to remind people raise hand is under reactions. I could never find it.
I'll go ahead and ask a question then. So in your, I think it was in objective 1 or 2, but you talked about going down to the 4.2 CMS. Is there, we haven't seen that since what, the 70s or 80s. That corresponds to like 150 CFS. What was the reasoning behind that?
Well, we just had capacity estimates at that flow rate based on the range of output that we got from Nate. So we decided to include that in our analysis because it may be relevant in the future if flow management ever decides to change to something more natural for lower flows in the summertime. Does that answer your question?
Yeah, that's, I kind of, yeah. Does anyone else have any other questions? or comments? Okay, go ahead, Chad.
Hey, Emily, can you go back to your recommendations slide?
Yes.
Under the managed flows to increase capacity during the rearing period, if we ultimately are able to shift some of our rod water to the winter period, is there a quick and dirty rule for where we should be trying flow ranges we should be trying to avoid during that rearing period?
So quick and dirty, I would say anything greater than 1500 CFS from the dam, because at that point, that's generally where you start to see the positive relationship between capacity and flow. And then, you know, of course, it will be greater than that as you move farther downstream from accretionary flows. So yeah, I think that right around there is typically where you're starting to get out of that habitat dip.
Yeah, and if we're working with lower or smaller volumes of water and we aren't able to achieve the minimum 1500 CFS, or we just want to see variability within the hydrographs that we're implementing, do you have any recommendations for lower flow volumes?
Well, I think that, you know, this capacity metric is very informative, but there's, like I said, in the recommendations, there's other important variables that aren't captured in the capacity metric that may be telling a different story of how beneficial those lower flows or mid-range flows are. So I think I can't directly answer that, but I think there's a little bit more that goes into how fish are benefiting from certain flows.
Thank you.
Hey, this is Brant. Could you say Emily, what 1500 CFS is in CMS, please? I just have troubles, and you guys, you know, I'm old, and you know, Dave brought up, you know, 56 CMS is 2000 CFS. You just said, you know, do 1500 CFS or greater. I just have a hard time that quick translation.
It's 42.5 CMS is 1500.
42.5. Cool. Thank you.
And then, yeah, 56 would be 2000.
Yeah, you know, dam management, it seems like it's all in CFS, so it's helpful for us scientists to, you know, figure out what CMS is. We all use it, but yeah.
Yeah, it always gets me every time.
Does anyone else have any other questions or comments? Okay, well, thanks a lot, Emily and Dave and Aaron, for that presentation. We can move on to Josh, who's going to give our final one of the day about the systemic base flow habitat mapping.
Good afternoon, everyone. Let me know if you can see my screen.
Yeah, you're good, Josh.
Okay. So we're going to have to backtrack just a little bit. The first talk by Ruben talked about, you know, habitat that had been physically mapped in the river. And then we transitioned to Emily, and she was talking about capacity, which is different. And now we're going back to the same sort of categories that Ruben was presenting. And so what I've got today is some analyses of summer base flow rearing habitat across the 40-mile restoration reach. I did not use kilometers, I used miles. And so although this is a culmination of a project that started in 2009, a large part of the data that I have today should be considered preliminary because it has not been peer reviewed or properly written up and published. And I had to sort of cherry pick data from an unfinished report. Anyway, thank you for being here. So Ruben presented site evaluation scale studies, which is on the top of this slide. And now I'm going to present the systemic evaluation of rearing habitat across the 40-mile reach. And just to refresh your memory, we map habitat by measuring depth and velocity and distance to cover using GPS equipment and flow meters. And we literally map the surface area of the river that meets our criteria for rearing habitat. And those
Hey, Josh, could I just, am I the only one that's not seeing his presentation? Is it, all I see is your, is the actual view of the PowerPoint. It's not the actual presentation screen. If you have multiple screens, sometimes in order to share your screen, you got to select the right screen that the presentation's on. It could just be me. But as you're progressing the slides, I'm not seeing the progression.
All right, let me try again. How about now?
I'm seeing, all I'm seeing is the actual program.
Yeah.
I'm not actually seeing the full. Am I the only one that can see?
No, I
that?
see
Or that's not.
Chris.
What?
I'm seeing
Yeah.
your presentation view.
Brant, you can see the presentation view. If that's the case,
No,
I can.
I actually saw so I saw two screens, I think. I think he,
Okay.
yeah, it wasn't as good as it could be.
Okay. How about that?
Yeah, that well.
Now I'm seeing the your.
What is that?
Do you have multiple screens up, Josh?
Yes.
It does it give you an option of which one to select when you go to share screen in Zoom?
I've chosen both of them at different times.
Oh, okay.
Well, do what you just did, like with PowerPoint, but switch the screen that you're sharing, and then it should work. Nope, I lied. Hold on. Escape that. Go to slideshow on your tabs. And then turn off to the right of where you are, so where it says use presenter view, turn that off. Now try to turn it on. So now it only shares the.
All right, are you guys seeing the title slide?
No, we still see like you're going to edit your PowerPoint presentation instead of the actual slideshow.
Okay. This is crazy. When I click share, it shows my PowerPoint in two different available screens.
So if you hit on your PowerPoint, start your presentation before you start sharing your screen, and then go to the whatever version this is, Teams or Zoom or, and then you should be able to see then you just pick one screen, the one that actually has the presentation on it, because it should display that.
It's crazy.
Or just go with it.
Yeah, I blame Zoom.
Whoa, this is so crazy. All right, let's try this. How about that?
If only.
No?
You're very
This will-
consistent on what you're displaying. Hey,
There it
that
goes.
worked. Yeah, you had it.
There?
Success.
Yep, there it is.
That's your slide number 2.
Okay. All right, great. So yeah, I'm systemic evaluation across the 40 miles. I was talking about how we map the habitat. We measure the surface area that meets our habitat criteria. These are the criteria that we use for 2 life stages, fry and pre-smolt, based on size, for depth, velocity, and distance to cover. And we end up with these categories: optimal, and then everything combined is total habitat. Everything I'm presenting today is data that were collected at summer base flow, or 450 CFS. And these are our 400-meter grits sites, and they are spatially balanced and randomly selected according to the grits protocol. And they are 400 meters long each. And sometimes they overlap rehab sites and sometimes they don't, which you can see in this map. This is a rotating panel revisit design. The first part of the presentation, I'm going to present those years of data, and then we'll transition to combining them all into one. Each of those 5 panels is comprised of 16 400-meter sample units. And so all the panels combined cover about half of the restoration reach. Has restoration caused change in rearing habitat at the restoration reach scale? The hypotheses that we are trying to either support or deny are: restoration efforts create measurable improvements in rearing habitat area over a 5-year period. And 2, annual peak stream flows, particularly those greater than 6,000 CFS, will improve rearing habitat, with larger improvements stemming from higher magnitude events. And these were derived from a couple of foundational documents for the TRRP that you can see at the bottom of the screen. We found that pre-smolt and fry habitat areas are highly correlated, and so I will only be presenting pre-smolt habitat. Yeah, this thing is like right in the way. So yeah, between 2009 and 2013, there was really no change in base flow rearing habitat. If you look to the right on this table, you'll see some numbers that are in bold font. Those are significant changes. And so if it has a negative sign, that means there was a decrease in habitat, either for optimal or total. And if it's a positive sign, then that means there was an increase. And so there was a little bit of both. And so there was no net gain in habitat over the 2009 to 2013 period. Oh, sorry. Yeah, so the comparisons, if you look on the left side of this table, we've got the years that are compared. And the water year type, which covers almost all of them except maybe critically dry. You've got the peak stream flow that was experienced in that year or so period. And then the panel number, the differences, and then the far right column is the percent of the 16 sample units that showed an increase. This shows that there were localized changes in habitat, but there's not a real pattern according to stream flow, a peak stream flow. So you've got changes in increases in habitat at low flows, you've got increases in habitat at higher peak stream flows, and conversely, the opposite of both for optimal and total. And the authors of that first 5 years of data concluded that habitat improvements could be increased by synchronizing dam releases with tributary stream flow events, which is obviously a hot topic for the program currently. And so now we're going to revisit that rotating panel design and include subsequent years after 2013. So as a result of that initial 5-year analysis, the sampling design was changed. So each panel was not visited as often. And then also I'd like you to note that the bold X's for each panel indicate the sort of the long-term comparisons that I'll be making here in a minute. So the widest range of sampling efforts. So it's like 4 to 6 years, depending on which panel. So using the whole data set, the objectives were to identify predictors of habitat status, or what the habitat was at the most recent survey. And so that was across the 5 panels and 80 400-meter grid sites. Second objective was to predictors of change in rearing habitat. We included the longest revisit interval, which was from the initial visit to the most recent visit. 4 to 6 years was the range. And some of the factors or predictors that we included in our model selection were channel rehabilitation, so like the proportion of the grit site that overlapped a rehab site. We also categorized the grits sites into whether they were sampled before construction, during construction, or if there was no construction associated with that site. We also looked at the year of construction of the rehab site that perhaps overlapped the grit site. We also looked at stream flow magnitude and duration. We looked at the proximity of those grit sites to coarse sediment augmentation sites or to tributaries as a source of sediment. So the cutoff, we used grit sites that were within 500 meters of either a gravel augmentation site or a tributary. We also looked at the wetted area of the grit sites. We used a channel complexity metric and also a wetted edge length. And this just shows the daily average stream flow over the study period, including some peak stream flows that exceeded a threshold of 6,000 CFS, which is represented by the dashed horizontal line. And so if you can see it, there's vertical gray dashed lines that represent when the surveys happened. And so they're, before and after some of these peak stream flows over the years. And so for objective 1, model selection process for pre-smolt habitat, you can see total habitat and optimal habitat represented here. And so wetted area was considered, it was an important main effect. And so we went through the Keikis information criterion process to sort of rank different combinations of those predictors to come up with a model that could explain the status of total and optimal habitat at the most recent survey. And we found that wetted area, along with channel complexity and year constructed, or wetted area, channel complexity, and the proportion of the site that overlapped the construction explained a lot of the results for total habitat. Likewise, for optimal habitat, we found that wetted area plus distance from dam explained the patterns there. And then this just shows the parameter coefficients, including interactions for the selected models. So if I go back, there's model 1 and model 2, total and optimal. 1.1 for total, the difference being the, let's see, we've got the area, the complexity, year constructed, and then in 1.2, we have proportion constructed. And then for optimal distance, area distance to dam, and the interaction of area and distance to dam. This just sort of helps us kind of focus our thoughts on what can explain the habitat patterns that we're seeing. The channel complexity metric we used was from the phase 1 review, Buffington et al. 2014, and that's defined by edge length divided by the square root of wetted channel area. You know, at the time that this was adopted for this study, it was kind of the only thing that was available that was Trinity specific. Although in the subsequent years, we've kind of learned that there's some problems with that metric, and you know, Dave presented some newer stuff today during Emily's talk that would be probably more useful. This is just an example of a simple versus a complex sample site. So the one on the right has a lot more edge length and surface area as well. And this just shows the relationship between some of the variables and habitat. So that's the mean with the 95% confidence intervals for wetted area, channel complexity, and year of construction on total habitat. So for objective 2, we found that total habitat increased between the initial and the most recent surveys. Optimal, the signal wasn't quite as clear. And so for objective 2, we went through a model selection process similar to objective 1, and found that the change in edge length and the construction category. So the construction category, as I referred to earlier, whether or not there was construction that happened before the grit site was sampled, during, or if there was none. And then for optimal habitat, the change in edge length was identified as highly explanatory. And again, we have the parameter coefficients, and you can see that in addition to change in edge length, that if construction happened before if it happened during, so let me start over. If construction happened between the initial survey and the most recent survey, that drastically improved the explanatory power of that model. And so this is just showing model association of wetted edge length and category of restoration on change in habitat areas. So it's very clear, especially if you look on the right here, that if you rehabilitate the channel in between the times that you survey that particular reach of channel, there's more habitat. And the one on the left shows that essentially the same thing. I know those lines are kind of hard to see, but. So the conclusions basically from this are that the habitat status at the most recent survey can be explained by the wetted area, channel complexity, and then some aspect of construction. And similarly, for objective 2, change in habitat between the initial survey and the most recent is best explained by the change in edge length, the construction category, and one of the results of that was that we identified total habitat as increasing between 2009 and 2016. One notable conclusion, I guess, is that when we considered stream flow as a main effect, it didn't really explain any of the changes in habitat that we observed, but it is, related to wetted area directly, and it's also a primary driver of, processes that affect channel complexity. Thank you.
All right, thanks, Josh. Do we have any questions for Josh? Yeah, go ahead, Kyle.
Yeah, thanks, Josh. I guess I wanted to ask a question about that last piece where the stream flow magnitude and duration didn't explain changes in habitat. And of course, we all believe that stream flow is the primary driver of fluvial process, but I wondered if your results suggested that wetted width was really being driven by construction or changes in wetted width.
Good question. I'm going to say yes. I wish that I was more familiar with the analyses that went into this, but I'm not. Based on the large influence of construction on, you know, everything that we did for this, I'm going to say that yes, it's probably because of construction.
Thanks.
Is that a new hand, Kyle, or still an old one? Does anyone else have any other questions for Josh? Yeah, go ahead, Brant. You're muted, Brant, if you're trying to ask something.
I sure was. I wanted to thank Josh first for the presentation. It's always good to hear some analyses on this. At the start, he was talking, or Josh, you were talking about these analyses are, isn't it all based on the base flow, this analysis? Because, and I'm just getting at this question that, you know, what would you suggest? That the real importance is the rearing period, as Dave and Emily pointed out, or I think they were making that point. How does this relate to when the fish are really there?
Yeah, that's a good, Brent. You know, 450 CFS is mostly in the summertime, and as we know, they're in the process of leaving the restoration reach, you know, before and during that period. So, you know, way back when it was sort of picked as an index stream flow, but obviously it doesn't quite match up to, you know, how the stream flow is managed. Yeah, like the March, April, May period is not really reflected in this.
Right. So how do we, it seems to me that there would be better, you know, it'd be better, but I can't say that, you know, with this presentation, I don't think. Can you have any guidance on, what, you know, what works for those? So they flows besides the capacity stuff that has been talked about?
Yeah, I mean, that's the obvious kind of direction we're going. And I think that power of the hydraulic modeling along with capacity estimation will help us get beyond this. You know, this is, like I said, this is a culmination of a project that started a long time ago. And in the, you know, in the interest of being thorough and continuing following through on stuff, we need to, you know, synthesize these data, but obviously we have better tools now that can address questions about the critical period.
Mm-hmm. Okay. And maybe that gets at stream flow magnitude here.
Yeah, I mean, I guess if you're just kind of talking about stream flow magnitude and how it creates complexity, you know, I think the similar conclusion that was made after the first 5 years is that, you know, we don't have the stream power we necessarily need to move stuff around and kind of create that dynamism that we know rivers can display. And so this idea of synchronizing dam releases with tributary accretion is, you know, that's the direction we're headed.
Yeah. Okay, thanks.
Do we have any more thoughts for Josh? All right, I'm not seeing any, so I guess with that, we'll conclude our session for today. We have another one next Thursday this one's at 10 a.m. So it's an earlier one. And that's going to be about the juvenile adult salmonid synthesis reports that are either finished or ongoing. So We will see everyone next Thursday at 10 a.m.
Thanks,
Chris, I have a, oh, sorry, go ahead, Aaron.
I was just saying thank you.
I was wondering, I noticed that these are being recorded. I had some interest in some other symposiums that were presented earlier, and I wasn't able to participate. I was wondering if these recordings are available.
Yes, they are. They are on the TRRP website. If you go under the, I believe, adaptive management tab, they should be listed there. If not, I should probably just send out a link to everyone. But there is a page for all the synthesis reports and the these talks.
Great, thank you, and thanks for putting it on. This is some great talks here.